Works? Great. Well, thank you very much, and thanks to everyone for coming and all the speakers, yeah, thanks for participating in this conference. So I'm going to first remove this window somehow, hopefully. Yeah, okay. And then I'm going to talk about batching techniques for accumulators with applications to blockchains and IOPs, and this is joint work with Ben Fish, who's also a PhD student here at Stanford, and our advisor Dan Benet. And I will mostly focus on the blockchain application, but thankfully Ale and Ellie did such a great talk in talking about IOPs, and I will talk in the end, give a little bit bonus information of maybe how we can make these proofs even smaller with the techniques that I present today. But the main thing that we're going to focus on today is the Bitcoin state and this application of accumulators to Bitcoin and blockchains in general. So the Bitcoin state is the UTXO set, so the number of coins basically that are currently unspent. And it turns out that this set is the more people use Bitcoin and also the more transactions happen with small dust, the larger and larger the set is growing. And if you think about consensus at a more abstract level, what we have here is something called stateful consensus. So all of the miners or all of the validators that participate in the consensus need to store the entire state because they want to be able to verify a state transition, say a new transaction. And if they didn't store the state, so if they tried to do stateless consensus, well then a new transaction came in and they wouldn't know whether this transaction was valid because they don't have the state to verify whether this transaction is valid. So for example, very concretely, if this is a coin, then how do the miners know whether this coin has been spent or whether it has, whether the coin is spent or whether it's unspent? So by the way, these beautiful animations, which are not as good as Ellie's, are thanks to Ben, but the solution to this stateless consensus problem is something that we've heard a lot about in this talk. It is proofs. So what if the users, or what if the person that provides a transaction, that proposes a state transition, provides a proof that the state transition is correct? And all of these validators and miners who don't store the state, so they only have a small commitment to the state, can then check the proof and verify that the state transition is correct. So the work has kind of been shifted from the miners and the validators to the users who store and maintain these proofs. So the question is, of course, what do these proofs look like? How are they generated? Do they require a state? Who generates them? And so on and so forth. But what this general paradigm does of having a transaction which proves that it's correct with respect to the state is remove this dependence in the consensus. I can participate in the consensus, and we want our consensus to be very decentralized. We want many nodes, for example, to participate in the consensus, and it removes this burden to store the entire state here. So let's look at a very, very concrete example of a consensus system, mainly something like Bitcoin, where, and I will talk about other systems later on in the talk, but let's focus on Bitcoin for the first part of the talk. And in Bitcoin, the state is this UTXO set, which miners agree on. And if I want to commit to the UTXO set, and I can do that in something called an accumulator. And an accumulator is a commitment to a set. So I have this set of UTXOs, and then in every transaction, I provide a proof that the UTXO that I'm spending is in fact in the UTXO set, so it is unspent, it is a UTXO. And then the set needs to be updated, of course, with the new coins that were created and the old ones which were spent. So in general, the accumulator, an accumulator has these following functionalities. You can add things to the accumulator, you can also remove things, and you can provide inclusion proofs, and then a miner or a validator can just take the transaction, or this X, and the inclusion proof and the accumulator and verify that these proofs are short. And the important thing is that both the accumulator state and the inclusion proof are short, And one example of an accumulator, one very concrete example is that you may be very familiar with, are Merkle trees. But later on, I will talk about these RSA accumulators, which have the benefit that the inclusion proofs are constant size. So again, the blockchain design would look like this. You have in every block now, you have this accumulator, which commits to the state. And then, so how does this look if we have a Merkle tree? Well, then the Merkle trees have very nice properties. The Merkle tree root would be stored in the block. It's constant size, and the inclusion proofs are logarithmic in size, and you can even do exclusion proofs if you sort the tree. So the transaction would then contain the proof, and the miner can verify. The problem with Merkle trees, though, is that if we have all of these Merkle tree witnesses which need to be communicated, well then this really increases the communication by a lot. So say for 100 million UTXOs, this would increase the communication to 100 gigabytes. And these things need to be stored with the users. The miners don't have a lot of storage now, but we've increased the communication by a lot. So that may not be what we want. So what we would want is basically something, we already have these short membership witnesses per items. We would like something that is efficiently updatable. We want efficient verification. And then there's also these questions like, say I have multiple proofs. I also say witnesses sometimes interchangeably here. Say I have multiple proofs created by multiple users, so for different transactions. Can I somehow aggregate them into a single proof? Is there some way that I can combine these proofs? Or can I verify multiple proofs faster than maybe verifying one proof? So in our construction, we're going to use RSA accumulators, which have been around since the early 2000s. And you can view them as a drop-in replacement for Merkle trees if the Merkle tree is used as an accumulator. We'll talk about another use of Merkle trees a little bit later. And these accumulators, they work in these so-called RSA groups, and what you have to do is you have to choose an RSA modulus, n, which is the product of two primes, and it's very important that these two prime factors are thrown away. This is a trusted setup. And the other thing that I need is I need a hash function which maps my elements to primes, okay? And then I initialize the accumulator with just a so-called generator of the group. And my talk, just as Alice's talk, is also going to be a little bit technical, but I hope that you can still follow along with the important points. So how do I add something to the accumulator? Well, it's very simple. I just have my current accumulator state. I map the element to a prime. We will later see why that is important, that it is a prime. And then I raise my current accumulator state to the element, to the mapped element, and then I get my new accumulator state. And deletion, deletion is somehow opaque, but you basically just take the element's root, so you just do the inverse. I'm actually going to start the presentation again, because it's kind of weird. Hopefully this works. Yeah. So you just take the element's root to do the inverse operation. And it turns out that that is actually, it looks trivial, but the whole property that we need of these groups is that taking roots is hard. So we will talk a little bit about how can we take these roots if that is hard. So what is the state of the accumulator after I've done a bunch of additions? And I will omit the hash function for the rest of the talk. So if you think about it, if I have a set of elements S, or if I have my set S of elements, then the state of the accumulator is just the product of these elements, or the accumulator, the base element of the accumulator raised to the product of these elements. So for example, this is commutative. It doesn't matter in what order I add the elements, the state of the accumulator will always be the same, right? Because multiplication is commutative. So how do I then use this accumulator? Well, I can compute an inclusion proof, and the inclusion proof is basically just the state of the accumulator without my element. So I remove my element from the accumulator, and then that is my inclusion proof. And I can, for example, compute this using a trapdoor or reconstructing this accumulator. And then verifying is just a test add. I just add the element again, test whether I get back to the original accumulator, and if that holds, then this worked. And the nice thing about these inclusion proofs is that they're constant size. So the Merkle tree proofs grow logarithmically with the set. So for example, if my set is 1,000,000 things, then it's 20 hashes. If it's 1,000,000,000 things, then it's 30 hashes. This is always only one group element, so about 2,000, 3,000 bits. I can also do exclusion proofs, and this relies on these Bezout coefficients, so that there are these integers, x and a and b, such that a times x plus b times u is equal to 1. And these integers always exist if and only if x and u are co-prime. But if you think about it, this is why we map everything to a prime. If x is not in the set u, so if x does not divide u, then they have to be co-prime because they're distinct primes, and u is a product of other primes. So this is how I can do an exclusion proof, and you can also update these proofs very efficiently without knowing what is in the set. So I can update the proof in a stateless manner. So the state of the art is that I have these constant size inclusion proofs. It's better than Merkle trees for sets over 4,000. I can add things statelessly. I don't need to know what is in the set. And this could be used, as to store the storage. But there's room for improvement. So these batch inclusion proofs, there's this trapdoor which we talked about. I want to maybe delete something without knowing what is in the set and without having the trapdoor. And I want to verify many things faster. So this is this new work which Ben, Dan, and I have been working on. So the first thing is aggregating these membership witnesses. So say I have two proofs, pi1 and pi2, for two distinct elements x and y. So in our blockchain scenario, what is this? I have my transaction x, I have my transaction y, and both of them have a proof attached to them that these transactions are inside these coins that are being spent are inside the UTXO set. So these are completely independent proofs. But it turns out, well, they're not independent, they're with respect to the same accumulator, so they're the same state. It turns out that I can use kind of the same trick, these Bezout coefficients, to combine these proofs, and this is also referred to as Shamir's trick, after the S in RSA. And it turns out that I can combine these proofs to be the xyth root of A. So basically it's an inclusion proof for x times y. But if you think about it, an exclusion proof for x times y is the same as an inclusion proof for x and y. I will only be able to construct an inclusion proof for x times y if x and y are in the set. But this inclusion proof, this combined inclusion proof, is still one element. So I took two proofs, combined them into one. And I can just repeat this over and over again, such that, for example, a miner could take all of the transactions in the block and all of the inclusion proofs, all of the membership witnesses, and crunch them together into one single membership witnesses. So this is similar to the aggregation that you, for example, have for BLS signatures, where you can non-interactively aggregate all of these signatures. So all of these witnesses, all of this overhead for Merkle trees, which would be one Merkle, if you use Merkle tree, it would be one Merkle tree proof for transactions. If you use RSA accumulators, it's just 3,000 bits for a single block. And there's even some aggregation that you can do across blocks. But the second problem that I'm going to talk about is this trusted setup. So I need this n, which has these unknown factors, p and q. And efficient delete actually needs a trapdoor. And you can find some n's in the wild that are where no one probably knows this factorization. So for example, there are these RSA numbers which were created as challenges, and they've been around for 30 years, and I think Ron Rivest, who created them, says he threw away the factorizations. So if you trust that, you can use these n's, or you can use some multi-party computation. But there's also an alternative approach, which has been proposed before for accumulators in 2012, which are these class groups of imaginary quadratic fields. And these are just mathematical objects that basically have the same, they function in a very similar way to these RSA groups, in that it's also hard to take roots in these groups, and I don't know the so-called order of the group. And if I want to achieve 128-bit security, they're actually even a little bit smaller. But they're much less explored, and so that is a downside. But they don't have this trusted setup. I don't need, I can generate them from a publicly known string. So how do I, when I don't have this trapdoor anymore, so I can delete with a trapdoor, right? Using the knowledge of P and Q, I can take roots. But how do I delete if I don't have this trapdoor? Well, let's think about when I want to delete. Well, I want to delete a coin, for example, from my UTXO set whenever it's being spent. But when it's being spent, that is exactly the time when before it's being spent, I need to receive an inclusion proof. So I only really have to delete when there's an inclusion proof. But if we think about what the inclusion proof was, the inclusion proof was exactly the accumulator value without the element. So the inclusion proof is exactly the accumulator with my element deleted. So deleting is very, very simple if you have an accumulator. It gets a little bit more complicated when I have two things that I want to delete from the same accumulator at the same time. So sort of in an asynchronous setting where I have multiple transactions that are spending from the same accumulator. It turns out that the same trick that we used before to combine the inclusion proof here serves us again. So we combine all of these inclusion proofs into a single updated inclusion proof, and this will be exactly the accumulator with all of the items removed. So again, this operation that we already wanted to do, which is to batch these inclusion proofs, helps us delete elements from the accumulator without knowing, right, this is, what do I mean by stateless, is I can delete without having any idea what is in the accumulator, or what else other than the elements that are deleted are in the accumulator. It doesn't matter if there's a billion things in the accumulator, I don't care about it, I don't need to store it, I can now delete, and I've previously shown you how to add things to the accumulator. So no state, no trapdoor, and no synchronous. The other problem is that these accumulators are sort of expensive, you know, not crazy expensive, but maybe I can do like 600 operations per second on my computer, and with class group there's been, I don't have the results, but there's been a competition on actually implementing them very efficiently, done by Chia for VDFs, and so, you know, we're getting better class group implementations, but these things are still kind of slow. And especially for the verification, which many people have to do, only one person has to create the accumulator, but many people have to check that it's correct. So can we do something better? Can we somehow outsource the computation here? So luckily there's this beautiful proof designed by Benjamin Veselovsky for these verifiable delay functions. I'm not going to go into them, but basically it's a proof that x raised to a gigantic number is equal to y. And the whole point of this proof is just efficiency. It is kind of like Ellie talked about, this is not about zero knowledge. It's about achieving efficiency. So how can I prove to you that x raised to this gigantic number, this would take t steps normally to compute, is equal to y? Well, it turns out that you can run this protocol, and then the verifier can verify this protocol in only log t steps. So it's almost log of the exponents. So very, very efficiently, you know, computing it takes 1,000,000 steps, verifying it takes 20 steps. So this verification is very nice, but it only works if the exponent is 2 to the t, so a so-called smooth number. So it is a 1 with a bunch of zeros in binary. So we considered the problem if we think about what do we have to do or what do we have to check in these accumulators, well, it is our accumulator raised to some more complex number, some arbitrary number, the product of a bunch of primes. It's not smooth, it doesn't look as nice and beautiful. So I just want to check now that x to the alpha is equal to y. Well, it turns out that basically the same protocol, though, still works. However, now the efficiency is log of alpha. So asymptotically, it's not necessarily better, but it turns out that in practice, with this proof, I can get a 5,000 factor speed up. So using this proof, right, so let's step back a second. There's a user, there's a miner who creates this accumulator, for example, or adds a bunch of things to the accumulator. And I want to check that his work was done correctly. And he will provide this proof of exponentiation. Then I will have to do work, which is a 5,000th of the work that the prover will have to do. So, you know, he can run on a very expensive Amazon EC2 instance, or, you know, use his proper hardware, and I can run on a little smartphone. So, you know, This factor of 5,000 matters. So what does this whole system now look like? How can I use this to achieve fast block verification despite being stateless? So I have the accumulator, and then a bunch of transactions come in, and I delete them from the accumulator using this batch delete property. And then I will add the transactions which, the new coins which are created. So my block has spends a bunch of coins, it creates a bunch of coins, and it has some signatures, and then it has these updates to the accumulators and attached with the proof of experimentation. So the verifier here still needs to check all of the signatures and check all of the transactions. This is sort of an orthogonal problem. You could use snarks and other techniques and recursive snarks to solve this problem. But that's sort of orthogonal. We're really concerned about the space and about this check that our coins are unspent. And here now the verifier just has to check these proof of exponentiations, which are really, really fast. So what is the performance? Take this with a huge grain of salt. This is done like micro benchmarking on my laptop. But with Merkle trees are just very fast. I can do 100,000 transactions per second. With adding, we get to these 600 transactions per second. And verifying, checking the POE is actually even faster, way faster than the Merkle trees themselves. The most expensive part now is mapping things to primes and doing primality checks. So there's actually some interesting maybe things with primality check. I have to do a bunch of batch primality checks here. But that actually takes up most of the time, but I can still do about 20,000 transactions per second this is on my laptop here, and not a good implementation. And with class groups, I guess, we still have to get these numbers, but now at least there's been a lot of work on improving these implementations. So what about accounting systems? I talked a lot about, UTXOs and set commitments. Accumulators are commitments to set, but that is only for these very simple Bitcoin-like UTXO systems. A lot of currencies these days, or a lot of general systems, are more like accounts, especially if they're smart contract-based. And each account stores some information about the account, say a balance. And in general, the way that I would implement this is using a so-called vector commitment. So the index of the vector commitment so I prove to you that at a certain index, at a certain account, the value of the commitment is some other thing, right? It's a positional proof. And it turns out that the simplest vector commitment that you already know is a Merkle tree. A Merkle tree, I can prove to you that the ith element is some value, and I can only prove to you, that there's no other thing which I can convince you is at the ith position. So here the property, the vector commitment has the functionality of opening the vector commitment, and we in our construction design so there's also this RSA-based vector commitment, which has, again, the nice property that it's constant size, but the problem is that I need these large parameters. So if I want to commit to a vector of size n, a million, then I need parameters that are linear in a million. The problem is with the accounts, I really want a massive number of accounts. I want actually an exponential number of accounts because most of these accounts have not been created yet. I want to be able to support future accounts that have not been created yet. So what we did is we used our accumulator to create a new vector commitment which has a constant size setup, so it doesn't have these downsides, and also has our similar batching properties as the accumulators. And the idea is simply that for every index, I have a prime, and it's a bit commitment, so I only commit to 1 or 0 at the index. And if the prime is in the accumulator, it's a 1 at the index, and if it's not, then it's 0. So if I then want to prove to you that, say a bunch of indices, so maybe a whole word is equal to something, I need to give you a batch membership witness, a batch inclusion proof, and also a batch exclusion proof. And there's a big part of the paper is focused on this batch exclusion proof, which uses some new interesting techniques. But with this vector commitment now, I can prove to you that large messages are in this vector commitment, again with a constant size proof. So if we look at the comparison to Merkle trees, our proofs are smaller. We have these batch inclusion proofs. the downside to the benefit of Catalona Fiore is that we can support an arbitrary number of accounts or indices because our setup is constant, versus theirs is linear. So for example, we can have these sparse vectors. Our proof of work, though, because we only have these bit commitments, is a little bit more expensive. So now it comes to the connecting back to the two previous talk, and thankfully we already heard a lot about IOPs. So the idea there is, right, I send you a very long proof, or the way that I instantiate these IOPs is by committing to a long proof. Then I get these queries, which are structured in some special way, and then I open you this proof at these certain points and give you inclusion proofs, so Merkle tree inclusion proofs. But basically, this is just a vector commitment. What I use here is a vector commitment. So I could use a vector commitment, like our vector commitments, to commit to these long proofs, and then using our batching techniques, I don't have to send you one proof per index, but only one proof overall. And in some very back of the envelope calculation for Starks for a very large instance, this would maybe reduce the proof size by a factor of 3. So maybe this can push the dexes from the 10,000 transaction to, because of the nice scaling, maybe we can get to 10 million transactions or something like that. But obviously this also has downsides, because here I do not get these nice properties that everything is just based on hash functions. These commitments, for example, one very severe downside is that A, they're slower to construct, and B, that they're not quantum resistant. So they're in fact very vulnerable to quantum computers. But it's a trade-off. So the takeaway point for the blockchain system is that I can shift away work from the consensus to the users, and in fact the users can split up storing the state in different ways. It isn't that every user now has to store the entire state. A user can just store the part of the state that they care about, or they can outsource the work to some other parties, and in general you can sort of load balance the work anymore. Load balance the storage much better with this separation of consensus and state. Yeah, so I think that is it. So if you have any questions, thank you very much. Yeah.
Questions for the speaker?
I wanted to ask about calculating roots. Are those hard because they're as hard as discrete log, or are the two unrelated?
No, it's more that the number of elements in the group are unknown. It is more related to the fact that I don't know how many elements are in this group. It is a different problem from, or I guess the connection is sort of unknown between discrete log hardness and this.
A couple more questions. So for h of x, since x is public and h can be calculated, anybody can generate an inclusion proof, not just necessarily the coin owner. Is that correct?
Right, and probably many users would outsource the work of generating these proofs to some service provider, but it's really these consensus nodes don't have the requirement. Now we're kind of forcing them to store the entire state, and with this we can separate these things.
And so for h of x, how do you construct a hash function that maps onto primes? Presumably that's non-trivial.
No, you just repeat the hash function until you hit a prime. So you just iteratively hash until you hit a prime, or you hash but it's actually, we have a lot of optimizations here where you can optimize, the prover can give you some hints such that the verifier doesn't have to do all of this computation again. So if you look in the paper, we have some optimizations for this. But the simplest way is you literally just iterate, because primes are, there's a dime a dozen.
That makes sense.
I have a question. How do proofs stay constant? Like, are they not unbounded? Do we take them modulo n?
Yeah, so that is a very good question. So the question is, how do we take them constant? So these multiplication in this group, say we use integers n, then the multiplication means a times b mod n. So a times b mod n will always be less than n. So no matter how many things I combine or multiply with each other, it is always reduced mod n, so it always stays constant size.
But then I still need to remember all elements which were included in the set in order to be able to prove exclusion.
To create the exclusion proof, I do need to know all of the elements in the set.
Okay.
But once I have an exclusion proof, and this is, I only link to this, you can update the exclusion proof statelessly. So I see, new transactions coming in, and I can update the exclusion proof without remembering what else was in the set. So we can talk about this offline.
For the vector commitment, is there something that can be done if you want to commit to more than a bit, or do you have to break it down into bits?
So for there's probably not without losing a lot of efficiency in other places. But what you can do is actually not for the IOP case, but for the account system case, what I can actually do is I just commit to one single bit. Does this account exist or does it not exist? I use a hybrid construction. I have an accumulator which stores the information about the state, and the vector commitment will just store the single bit of does the account exist or does it not exist. And if sort of all the additions are governed by consensus or done by a challenger in a more formal way, then this construction is still secure, where the vector commitment only stores a single bit and the accumulator stores the actual information.
But for a field element or things like that, I have to break it down into bits.
Yeah, for a field element, we don't know. This is an interesting open challenge, can we do something better?
Thank you.
So let's thank the speaker again.